Welcome to this explainer. Today, we're diving straight into the mathematics of equilibrium. Specifically, we're going to break down exactly how engineers calculate the true centroid of incredibly complex composite structures. You know, we all realize how absolutely crucial these kinds of calculations are for things like cantilevered bridges or asymmetrical machine parts, so let's just jump right into the methodology. Imagine trying to perfectly balance a completely irregular, odd-shaped object right on your fingertip, right? Now, for a flat, uniform circle or a perfect square, it's super intuitive. The balance point is smack dab in the middle. But what happens when you have a piece of structural steel with weird cutouts, varied thicknesses, and asymmetrical flanges? Well, today we are going to explore the mathematical solution to this physical challenge, a really cool technique that takes what looks like impossible calculus and turns it into straightforward arithmetic. Okay, here's our roadmap for today. First up, we'll look at the centroid concept. Second, the composite parts formula. Third, we'll walk through the three-step method. Fourth, we'll deal with negative area. And finally, we'll wrap up by calculating 3D composite objects. All right, let's kick things off with section 1, the centroid concept. To begin our deconstruction, we really have to define our terms here. For a flat, two-dimensional plane, a centroid is basically the exact coordinate where the moment of area is 0. What that means is, if you were to put a tiny pivot under that exact point, the object wouldn't tilt in any direction. And what is absolutely crucial to keep in mind here is that for any object made of a uniform, homogeneous material, this geometric centroid is literally identical to its center of gravity. Moving right along to section 2. The composite parts formula. So, instead of getting bogged down in heavy integral calculus to find the center of some unpredictable shape, because let's face it, nobody really wants to do that, engineers prefer a much more elegant solution. We use a weighted average formula for shapes that can be broken down. You simply take the sum of the centroid of each individual part, multiply it by its area, and then divide all of that by the total area of the whole shape. You do this once for your x-axis and once for your y-axis. It is just brilliantly simple. Which brings us nicely to section 3, the three-step method. Now, this mathematical theory translates into a highly visual, foolproof three-step procedure. Step 1, you break the complex shape down into smaller parts whose properties we already know. Think basic rectangles, triangles, or circles. Step 2, you find the area and the individual centroid of each of those new, simple parts from a common axis. And step 3, you just plug those numbers right into our weighted average formula to find the overall centroid. Let's actually apply step 1 to a complex T-section to see how this works. Instead of racking our brains trying to calculate the center of a T, we just establish a common y-axis right down the middle and an x-axis at the very bottom. Then we break the T down into two totally simple rectangles. So we get a 100 by 30 millimeter horizontal rectangle sitting on top and a 30 by 150 millimeter vertical rectangle below it. Suddenly, finding the center of each of these two individual rectangles, it's just basic geometry. For step 2, organizing your data into a standard table is absolutely essential. It kind of acts as a guardrail, minimizing your chances of making a mistake. By listing part 1 and part 2, then calculating their individual areas, their x-coordinates and their y-coordinates, you can easily just multiply straight across the rows to get your area times x and area times y values. That bottom row, it gives you the exact totals you need for the final formula. You just divide the final total of the a times x column by the total area, and boom, you have your overall x-coordinate. All right, let's tackle section 4, dealing with negative area. So, what exactly happens if our shape has a giant piece missing? Well, the good news is, a hole in a structure doesn't break our math at all. You just treat it as a distinct subshape. Let's say you have a large steel plate with a circular hole drilled right through it. You'd calculate the large rectangular plate as one solid part with a positive area. Then you calculate the circle exactly as you normally would. But here's the trick. You enter its area as a negative number in your calculation table. When you sum up your columns, that negative area naturally subtracts from the total, which perfectly shifts the centroid away from the missing material. And finally, section 5, calculating 3D composite objects. Stepping into the third dimension is actually a breeze, because the exact same methodology applies. Instead of multiplying an x and y coordinate by a two-dimensional area, we simply swap out the area measurement for volume and add a z-coordinate axis to track the depth. Even better, if you have a 3D object made of totally different materials, say a steel wedge attached to a block of lightweight concrete, you just swap volume out for mass or weight. The weighted average formula works exactly the same. instantly revealing the true center of gravity of a multi-material object. So calculating the balance of the universe, or at least the physical stuff in it, is really just a matter of basic math. That bookshelf, your desk, even the chair you're sitting in right now, they can all be deconstructed into basic rectangles, cylinders, and negative cutouts. Once you see the world this way, it's kind of hard to unsee it. So I'll leave you with this thought. Look around your room right now. How would you break down the objects around you into composite parts to find their true center of gravity?